Hi, my name is Nathan Annenberg. I'm calling from my office in New York City. I wanted to make this video because as an experienced math coach, I've tried to specialize in devising and implementing creative ways to learn mathematics to make it less threatening and more fun for young folks. Everywhere from the early childhood grades all the way through high school, even freshman college classes. I thought I was good at what I was doing. I've given workshops, I've created my own online course. But when I studied Vedic mathematics under Ken Williams, I suddenly realized I was dealing with a level of intelligence that was beyond human imagination, basically. The elegance of the algorithms, the imaginative way they were able to avoid lengthy formulas and procedures, the rapidity and efficiency of their strategies was truly impressive. So I began to learn more and more, and I began to incorporate them more into the workshops that I led and into my own classes that I'm teaching. Now, this particular issue that I'm starting with in this presentation is a really difficult one for most high school and freshman college kids, and that is memorizing trigonometric identities. It's not easy because there's so many of them. When I studied Vedic math, I was amazed because it just goes around the whole thing, has their own algorithms. You don't have to memorize any of these formulas, just doing something called operations on Vedic triples, and you basically solve the same issue. I'm going to be giving two separate videos because each one is with a separate topic, but each one deals with getting rid of all the memorization of the trigonometric identities. So without further ado, let's get started. Okay, to begin, I'm entitling this A Gallery of Trig Identities. Actually, it's only part of the gallery. This is only a video part one. I'm going to be stressing something called formulas of angle increase or decrease, which most high school and pre-calc classes in freshman college have to memorize. So to get started, the main one is this, sum and difference formulas. Notice that if with a little imagination you might get some memory gimmicks, you can probably master it that way, but 6 of them, it's just not that easy to do. And just when you think you've had enough, you have to go to something called double angle formulas, which adds to this memory load. Notice in the cosine double angle, you have 3 variants, which you have to know all 3 when you do something called verifying trig identities later on. If you know Pythagorean identities and the variants, you might be able to figure out one connected to the other, but it's still quite a task. And just when you think you've had enough of this, you get the half-angle formulas, which, to be perfectly honest, scares even me. The way the complex algebraic fractions within radicals are presented, then you get 3 variants again at the bottom with the tan. It's quite a load. And like I said, this is just the angle increase and decrease formulas. Vedic math has a very neat way to get around all of this, so you don't have to memorize anything. So we're going to start with some classic examples. So we're going to start with a classic angle sum situation, solving the sine of 105 degrees. Now we should see this is a sum of angles. If you know your benchmark angles, it's going to be 60 plus 45. We're going to start with the classic Western approach to see how it's traditionally taught. So as is usually taught, the teacher will present the general formula first, which of course the students have to memorize eventually. Then she will simply translate the original problem into the general formula and plug in the values. Now at this point, I'm assuming the viewer knows enough about basic right triangles to know what the sine and cosine of these very basic angles are. So I'm going to just save time and fill them in. So these are the basic fill-ins for these angles and these particular degrees. Now, we make things easier by combining like expressions. So first, we're going to get one numerator for both expressions and then combine even that. So here, we'll just make it radical 3 over 2 radical 2 plus 1 over 2 radical 2. We combine the numerator. We have radical 3 plus 1 over 2 radical 2. And the math world, they don't like radicals and denominators. So we're going to just multiply by 1 as radicals. And you end up with your final answer as radical 6 plus radical 2. And the denominator is basically just 2 times radical 2 squared, which is 2 times 2, 4. And that's your answer for sine of 105 degrees. Now, in order to even begin to start this problem, you had to memorize this. We're now going to go to the Vedic approach, shows a much simpler, more elegant way to solve this. So what the Vedic people do is a whole different way of thinking about this. Even for those of you who understand what Pythagorean law is and the triples are, I want to show you how the Vedic sages thought about this. Where it's really interesting. We think about angles as degrees or radians. The Hindu sages had a whole different mindset. Let me show you what I'm talking about. Even though it's not to scale, I'm just going to put the 60 over here. And most of you who know trig probably know this. You have to understand, though, that in Vedic math, when you say a triple, you don't just say any order. I know that in the United States, when we learn triples like the 3, 4, 5 triangle, we always say 3, 4, 5. But sometimes we have to say 4, 3, 5, and there's a reason for that. So I'm going to go over that right now. In Vedic math, you have an opposite side, just like we do in Western math, and an adjacent side. However, they call it the adjacent side base, and they call the opposite side height. Hypotenuse stays hypotenuse. Now this next part is important. We must, to show a 60-degree angle, make the sides in a strict order. And it's got to be base first, height second, hypotenuse third. Now, why would we want to do this? Well, why should it matter what the order is? Because we have an interesting situation where by listing a strict arrangement of sides, you have defined the angle without having to say 60 degrees or let's say pi over 3. Why does that work? Well, I think a good analogy is 10th grade geometry. I don't know if you remember the proofs to make congruent triangles. One of them was called side, angle, side. Well, look at this. We have side, angle, side. If you have any triangle with a side of radical 3, a right angle in the middle, and another side of 1, you're forced to have a hypotenuse of 2. And therefore, your angle of 60 degrees is preserved all the time. So Vedic triples, and it's really interesting, it defines an angle by arranging the sides without mentioning degrees or radians. I find that fascinating because later on, as we're about to do, when we add triples, if we're going to add degrees, we're going to go back to those complicated trig formulas. Watch what the Vedics do. We're going to go to the 45-degree angle triple now. Just to make it easier to understand, I'll put 60 degrees here and 45 degrees angle here, all right? And to add triples, for those who don't know, here's the algorithm. It's product of column 1 minus product of column 2 for the first element. It's basically 1 minus radical 3. I'm going to rewrite it as minus radical 3 plus 1 for better visual convenience. Okay, now then you add the cross products for element 2. So that's radical 3 plus 1. Then you just go to the vertical product for the third one. So there is your triple for 105 degrees. Now, the problem was sine of 105 degrees. Well, you have to understand, let's go back to the triangle here. Sine is opposite, cosine is adjacent, or we could say sine is height. So all we got to do is just make this element 2 and 3. We just do radical 3 plus 1, the height over the hypotenuse. And to, again, simplify it, if you recall, we do this again. And lo and behold, we get the exact same answer as we did with the Western approach. Now, what I find fascinating about this is all you had to do was learn how to add triples. You didn't have to memorize sine A cosine B plus cosine A sine B, and you've got it. Now, when Ken teaches this, he makes it even faster. He says, why worry about element 1? That's the cosine. I could have written it like this, like Ken would say. And he goes like this. That's a little bit further on as you get used to this. I want you to master this first, but Ken's right, absolutely. Why put an element in when you don't need it? So that's something for you to consider later on. So I just wanted to show you a classic sum of formula here for Vedic versus Western. Look how much easier it is for Vedic. Now, I could do more and more sum formulas here. I want to make a digression first. If you use a little bit of creativity and originality, you can find that some angles that go beyond quadrant 1, you don't have to add anything. You could do something that's even faster. You can ask yourself 2 questions. What is the reference angle of that angle, and what is the quadrant of that angle? So we could ask, for instance, solve the cosine of 135 degrees. Now we could do the conventional way, get the triple of 90 degrees plus 45. But guess what? What if we try this strategy here instead? For instance, let me actually draw the coordinate geometry situation. Here's your 135 degrees, approximately this way. All right, you go like this. Here's your 180 degrees. So your reference angle for 135 is 45 degrees. So we could already write a triple for 45 degrees. However, it's quadrant 2. Well, quadrant 2 tells you the x-coordinate is negative and the y-coordinate is positive. So the triple just becomes this. And you're already done with 135 degrees. We didn't have to add anything. Now cosine is easy. Just do negative 1 over radical 2. And if you want, you could do this radical transposition again. And you basically have negative radical 2 over 2 for your cosine of 135. This is how powerful Vedic triples are. Sometimes you don't even have to add or subtract anything. We're not going to deal with subtraction in this video, but I'm just mentioning it for now. If you know that the angle has a reference and you know its quadrant, you've already got the triple. So let me give you 2 more like that. So for cosine 240 degrees, let's just draw the graph. It's going to be somewhere over here. The reference angle is 60 degrees. And the quadrant is 3. So our Pythagorean triple for 60 is this. Now quadrant 3, the x-coordinate and the y-coordinate are both negative. So we already have the triple done. We didn't have to add, let's for instance, 180 plus 60 and add the triples. It's already done. And cosine, it's simple. Cosine of 240 is negative 1 over 2. And that's it. Again, if Ken were teaching this, he'd probably go like this, because we don't need the middle one. But I still want you to get used to the basic triple concept first. But I want you to know this can make it even faster. And we can do just one more. Let's say tan of 330. Okay? You should see it's going to be somewhere over here. Okay, the reference angle is 30 degrees. Quadrant 4. The triple for 30 is radical 3, 1, 2. Quadrant 4 simply tells you, well, x is going to be positive, y is going to be negative, and we've got it already. And the tangent, it is negative 1 over radical 3, and if you wish, you can make it negative radical 3 over 3. And that's basically how you do these rapid ones where you have reference angles. It doesn't always work out that way, but if you can use it, great. So we're gonna go to one more example that's a little bit more advanced. We're gonna deal with radians only. Well, I may make angle equivalents for those who are not used to radians, but here we go. So the one I'm giving you here is going to be in radians, and it's going to be also a reciprocal trig identity cosecant, which you should know is 1 over sine. So what we're going to do now is we're going to find a way to get two radians that add up to 11/12. What you could do is we can think of greatest common factor as, let's say, something over 3 plus something over 4. And we're going to ask ourselves, well, we can make these into 12ths. What combination of third and fourths can make 11/12? So I guess you could do 2/3 plus 1/4 because that makes 8/12 plus 3/12. So now, since we have pi here as radians, we're going to have 2 pi radians plus 1/4 pi radians. So we're going to add these up. But for those of you who are not that familiar, I'll just put an equivalence here. If we know that pi over 3 is 60, then 2 pi over 3 got to be 120 degrees. And pi over 4, you should know, is 45. So we're going to add the triples up. I'll make it angles just to make it easier for some of you. Okay? Now, what we just learned, for 120, we don't have to add things up. Remember, we have a reference angle going to the x-axis of 60 degrees. So we just make a triple for 60 degrees. It's quadrant 2, so the x-coordinate is negative. 45 goes like this. We do the classic Vedic triple addition of column 1 product minus column 2 product. That'll be -1 minus radical 3. I would prefer to write this first. And then we have the cross product of radical 3 minus 1. And then we have 2 radical 2. Now we wanted cosecant. Be a little careful here. It's the reciprocal of sine, so it's going to be hypotenuse over height. Now I could multiply by the conjugate of this and get a simpler form. I'll leave it alone for now. I just wanted to show you what's done and how Vedic math makes even difficult things a lot easier. If we had done this Western way, we would have had to memorize the sine addition formula and then get the reciprocal of that. It would not have been easy. So this is the end of my video part 1. I hope this helped you. You don't have to memorize any sum difference formulas. Just do Vedic addition or subtraction, whatever the case may be.